Welcome students, this is Ravi Shankar. So today we are going to study about a law, and that law is Gauss Law. In our previous videos, for the past two videos, we have studied about the electrical flux, and in this law we are going to relate that electrical flux with the charge. So, Gauss law is a law. Gauss law is a law which relates, both electrical flux and charge. So, the law which relates the electrical flux is, we are stating it as phi E. And the charge is considered to be small q or the capital Q. How we can able to relate these two? You see, in order to explain this, say after deriving the formula, we will define this law. So, how we can able to get this law? In order to get this law, you consider a point charge. You consider a point charge. When you are taking or when you are considering this point charge, let us consider that point charge as Q. So I am representing it in a diagram. I am taking a point charge and that point charge is taken to be plus Q. See, what I am going to consider is, when a charge is taken, around this you are having an electrical field. The electrical lines of forces are acting radially outwards. Now, around this charge, I am considering a spherical surface. See, if I am considering a spherical surface means the size of the spherical surface may be of any value. So, this is sphere that I have considered around the charge. Sphere means I have considered that in a three-dimensional way. You consider a charge in air. Around that charge you consider a sphere just like a ball. So, if when you are considering this sphere, the sphere may be of any dimension. So, we are generally calling this sphere as an imaginary sphere. An imaginary sphere. When you are considering this an imaginary sphere, the surface we are calling it out as Gaussian surface, an imaginary surface around the charge which is enclosing this charge, around the charge, and the surface encloses this charge. That surface generally we are calling it out as an Gaussian surface, a purely an imaginary surface. And let us consider the surface that I have considered here is having what? Is having a radius small r. Now, what I am going to calculate it here? I am going to calculate the flux in this Gaussian surface. How the flux is given? Already we have studied that flux through the closed surface is given by, in our last video we have studied flux through the closed surface is equal to, or closed area is equal to phi E, which is equal to closed integral of E vector into dA vector. This is what we have studied it in our last video. If that is the case, when you are taking the dot product, what will be your answer? Then when you are taking the dot product, I can consider as phi E is equal to closed integral of modulus of E vector is E, modulus of dA vector is dA into cosine of the angle. Angle is the angle between the normal drawn and the direction of electrical field. I will be representing the value of theta here. You see, when you are considering this, I am taking a small area here on the surface. I am considering a small area. Let us take this small area as dA. When I am dropping the normal for this area, the normal drawn, the perpendicular drawn will be along this direction. It may be represented as n cap, or I can represent it out as dA vector. dA, the magnitude, multiplied with the n cap, so it is a dA vector. Now, when you are drawing, electrical lines for this charge, since this charge is a point charge, electrical lines will be acting radially outwards. Electrical field will be acting radially outwards. So, if you are considering this line is also an electrical line of force acting radially outwards. So, when you are considering this angle theta, the angle theta is equal to 0. Since electrical line and the normal drawn both are along the same line, normal are along the same straight line. Since they are along the same straight line, or since they are parallel, we can say that angle theta equal to 0. If that is the case, then I can say cos theta is equal to 1. If cos theta is 1, what will happen to phi e? Therefore, I can write phi of e is equal to closed integral of e into dA. Okay, now what I can do? See, when I am considering that small surface area, inside that the electrical field is considered to be uniform. Or I can consider like this: if you are taking the electrical field at this point at a distance r from the charge q, I can get the value for E using the formula E is equal to 1 by 4 pi epsilon 0 q divided by r square. And when I am integrating this equation, integral of closed integral of dA, dA is a small area. If I am integrating, I can able to get the whole imaginary surface or the whole imaginary area called to be Gaussian surface, which is in the form of a sphere. So I can write this as phi of E is equal to electrical field E multiplied with, what is this dA? dA is, integral of dA is the total surface area of the sphere. So the surface area of the sphere is considered to be 4 pi r square. So let us do one thing. Let us consider this as equation number 1. Let us take this as equation number 2. And let us consider this as equation number 3. Now you see the total electrical flux available phi E is equal to E into 4 pi r square. So if it is equal to E into 4 pi r square, what is the value of E? E is considered to be the electrical field at a point at a distance r due to the point charge. But we know that electrical field at a point due to a point charge is given by 1 divided by 4 pi epsilon 0 into q divided by square of the distance. Now you take this value and substitute in equation 3. Substituting for the value of E in equation 3, what you will able to get? Therefore, I can say the electrical flux phi E is equal to, what is the value of E? It is equal to 1 divided by 4 pi epsilon 0 into q divided by r square multiplied with the area value, it is 4 pi r square. You see, in the denominator you are having 4 pi, here you are having 4 pi and r square, so 4 pi and r square will get cancelled. If that is the case, the flux available phi E is equal to, what is the formula? You see, q divided by epsilon 0. So this formula states the Gauss law, or I can say this equation. Okay, this equation is called as Gauss law. Clear? We can summarize again. See, when you are considering this summarization, you see what I have done. What is Gauss law? Initially, I have told that Gauss law is a one, or Gauss law is a law which relates the electrical flux and the charge Q. So, by relating that, what is the answer that you are getting? The answer you are getting is phi is equal to Q divided by epsilon 0. Phi is the electrical flux, phi E. So, we are relating the flux phi and the charge. How they are related is given in the final step as the Gauss law. So, in order to derive this value, what I have done? Consider a point charge Q. So, I have taken a point charge plus Q. Now, in order to determine this flux, around this charge, I have considered an imaginary surface. That imaginary surface is a spherical surface. That imaginary spherical surface, and we are calling it out as a Gaussian surface, which is the Gaussian surface is a purely imaginary surface. Now, the flux through the closed surface, we have already studied. If you are having a closed surface, then the flux through the closed surface is given by phi E is equal to closed integral of E vector dot dA vector. So, I can say phi E is equal to closed integral of, I am taking the dot product, so E into dA into cos theta. What is this theta? Theta is considered to be 0 because from the charge, the electrical lines of forces are acting radially outwards. If you are considering a small surface area on the surface of the Gaussian value, the normal drawn to the Gaussian surface and the direction of the electrical field are parallel to each other, or both are along the same line. So we can say theta equal to what? So we can say theta equal to 0. If you are saying theta equal to 0, the electrical line and the normal drawn are along the same straight line. So cos theta becomes 1. Since cos theta becomes 1, what I can write phi E is equal to closed integral of E into dA. Integral of dA is the whole Gaussian surface area. The Gaussian surface is sphere. So for a sphere, the surface area is given by the formula 4 pi r square. So substituting, I can get phi E is equal to electrical field E multiplied with 4 pi r square. Electrical field at the same distance on that Gaussian surface is a constant. So we know that electrical field at a point at a distance r is given by the formula 1 by 4 pi epsilon 0 q divided by r square. Substituting for E in equation 3, we get phi E is equal to instead of E, 1 by 4 pi epsilon 0 into q by r square multiplied with this value 4 pi r square. So on simplifying, we can get 4 pi r square gets cancelled. So I am getting phi E is equal to q divided by epsilon 0. This equation is called as or representing the Gauss law. See, when you are considering this Gauss law or when I am explaining this Gauss law, I have taken a spherical surface, but this Gauss law equation is true for any arbitrary shaped surface which encloses the charge. Okay, so here I can consider a note. What is that note? This equation called as Gauss law is true or is valid, is true for or valid for any arbitrary closed surface or arbitrary closed shaped surface which encloses a charge. What do you mean by this? See, the Gaussian surface around the charge that you have taken may be of any shape. If, for example, if I am considering a charge plus Q, and around this charge plus Q, if I am considering an arbitrary surface like this, for example, I am taking this area as A1, then the electrical lines of forces acting radially outwards. What is the flux available? The flux available in the surface will be then equal to phi of E is equal to charge available Q divided by epsilon 0. Similarly, if you are considering another surface around this, of some other area A2, then also the flux available is given by the same formula. It relates only the charge enclosed and that of the electrical flux. So the Gauss law is true for any shape of the surface, any arbitrary shape of the surface. For that the Gauss law can be applied. So using this we can able to state Gauss law. So let us define. What is the definition or what is the statement? So I can say Gauss law states that. Gauss law states that. Okay, Gauss law states that if a charge, see small q or capital Q, whatever may be, if you are considering a charge q is enclosed by any arbitrary surface, is enclosed by any arbitrary surface, then the total electrical flux phi E, then the total electrical or total electric flux, that the total electrical flux is given by phi E through the closed surface is, through the closed surface is 1 by epsilon 0 times the charge enclosed. 1 by epsilon 0 times the charge enclosed. See, this can be written mathematically as flux phi of E is equal to, in general for a closed surface, we have written it out as closed integral of E vector dot dA vector, which is equal to the charge enclosed. Usually we can say like this: Q enclosed inside the Gaussian surface divided by the permittivity of the free space or vacuum epsilon 0. So we can define this Gauss law as, the Gauss law can be defined as or stated out as, if a charge Q is enclosed by any arbitrary surface, then the total electrical flux represented by phi of E through that closed surface is always equal to 1 by epsilon 0 times the charges enclosed or charge enclosed. So phi of E is equal to closed integral of E vector dot dA vector, which is, this is a general formula, which will be equal to the total charge enclosed divided by the permittivity epsilon 0. Hope you should have understood this concept. And very important 3-mark question called to be Gauss law. See, after studying this Gauss law, we have to discuss about this Gauss law. So the next concept is discussion regarding the Gauss law. So we have to go with the discussion. Discussion of what law? Discussion of Gauss law. See, I will be explaining it in general and then I will be going as it is in your book. See, in order to study the Gauss law, first of all we have considered a charge. After that we have taken what? After that what we have taken is, around this charge you are taking an arbitrary area, and the shape of that arbitrary area may be of any value. But for reference we will be taking what? We will be considering, or we will be taking a spherical surface. So the first point that you should know is, say what it is given in your book, we will see it later, but you have it in your mind first of all. First of all, this surface, what we are calling it out as Gaussian surface. This Gaussian surface is purely an imaginary surface. Purely an imaginary surface, the first point. Then the second, what should be? The flux available due to this charge inside this electrical field depends only on charge Q inside the sphere, inside the Gaussian surface. If you are considering any charge outside the sphere, see, if you are having a charge outside this Gaussian surface, then the charge, let us consider Q dash, then this charge won't contribute any flux to this closed surface. Similarly, the third point also we can say, if you are considering the flux, the closed, that is the electrical flux in this closed surface depends only on the magnitude of the charge, only on magnitude of the charge, and not depending on, and it is not depending on location. Yeah, at what position the charge is available, location of the charge. It is not depending on the location of the charge, but it depends upon what? It depends upon the it depends upon the total amount of charge that is enclosed. These are some of the general things that you should know regarding the Gaussian surface and the Gauss law. Okay, see, we will explain it as it is in your book now as point number 1, point number 2, point number 3, etc. Before that, whenever you are studying the Gauss law, you have it in your mind that surface in which you are going to calculate the electrical flux around the charge is an imaginary surface, a purely imaginary surface, what we are calling it out as the Gaussian surface. Then the second point that I have told is that flux available depends only about the magnitude of the charge that is kept inside the Gaussian surface. If you are having any charge outside, that charge won't give or won't contribute any flux to this closed surface. And point number 3, when you are considering the flux in this closed surface, it depends on the location of the charges, and it is not depending upon the it depends only on the magnitude and not depending on its location, where it is placed inside the Gaussian surface. It may be here, or it may be here, or it may be here, but the charge should be inside the Gaussian surface. Whatever may be the location, no problem. It depends only on what? It depends only on the it depends only on it depends only on the magnitude of the charge. Okay, now let us see what are the important discussions that was being given in your book by point wise. So let us consider the point number 1. What is this point number 1? See, in order to explain the total electrical flux through the closed surface, they are stating the same thing what I have told here. See, point number 1 is the total electrical flux. Okay, the total electrical flux through the closed surface, depends only on the charge, or charges enclosed, only on the charges enclosed, and any charge, already I have told, any charge outside the Gaussian surface, any charge outside the Gaussian surface, won't contribute any flux, or I can say will not contribute any flux to the closed surface or to the Gaussian surface. This is the first point that I have already explained to you. Sorry. Okay. Let us go for the second point. What is the point number 2? See, what does that point number 2 means? The electrical flux is, that I have told you as a third point. Electrical flux is depending only on the total charge enclosed and it is not depending on what? And it is not depending on the location. And it is not depending on the location, but it depends upon the total amount or magnitude of the charge that is available. So second point is electrical flux is, okay, electrical flux developed is independent of location of charges, independent of location of what? Location of charges. Then what it depends? You can say depend on the magnitude, the total magnitude of the charges. Total magnitude of what? Total magnitude of charges. This is point number 2 according to your book. Then let us go for point number 3. What is that point number 3? See, let us consider this equation again. What is that equation? See, the flux available phi of E is given by closed integral of E vector dot ds vector or dA vector, which is equal to, what is this phi E? We can say it out as, according to Gauss law, it is the charge enclosed divided by epsilon 0, that is permittivity. See, both of this equation, you just consider the equation that I have written it inside the box. Closed integral of E vector dot ds vector or dA vector is considered to be phi E is equal to charge enclosed divided by epsilon 0. Now, you consider this equation, both the left hand side and the right hand side. When you are considering the left hand side, this E vector that is available in the left hand side of this equation is due to all the charges available. But on the right hand side, you are having this charge is in the Q enclosed. This Q enclosed is only due to what? Is only due to the charges inside the sphere or inside the Gaussian surface. So that is considered to be point number 3. So point number 3 states that the left hand side of the equation, okay, point number 3, isn't it? Point number 3 states that the left hand side of the equation, you are having the electrical field vector E vector is due to the charges present inside and outside. That is the total charges present. Here, when LHS is considered, left hand side is considered, the E vector, the value of E vector depends on both charges inside and outside. Both or all charges available inside and outside. This is one point. But when you are considering the flux due to Gauss law, according to Gauss law, that is here, when RHS is considered, okay, when you are considering the right hand side, when RHS is considered, then we can say that the Q enclosed, the charge available, okay, that is the charge is only inside the Gaussian surface. Only we have to consider the charge inside the Gaussian surface. Outside the Gaussian, the charge outside the Gaussian surface is not considered or is not included. So this we are considering it as the point number 3. Let us go for the next point. What is the next point? When you are taking the Gaussian surface, see, the Gaussian surface cannot pass through an discrete charge. See, I am writing the next point as the 4th point, and the 4th point I am stating that, see, when you are considering the Gaussian surface, okay, when you are considering the Gaussian surface cannot pass through, see, after writing this I will explain, cannot pass through a discrete charge, cannot pass through a discrete charge. What do you mean by this? See, let us consider like this. See, I am having a positive charge plus Q here. and you are having another charge q1 or q dash here. Now, I am going to consider a Gaussian surface around this charge plus q. I can consider like this, or I can consider like this, no problem. But this Gaussian surface should not pass through this charge, discrete charge q dash. This is wrong. Okay, this third charge, the third Gaussian surface is not possible. If you are drawing an Gaussian surface around a charge, the Gaussian surface cannot or should not pass through what? Should not pass through a discrete charge. Why that is the case? Why that is the case means, in case of discrete charges, electrical field is not well defined. Okay, why this is the case? Why it cannot able to pass through the discrete charge? Since in case of discrete charges, discrete charge or a small point charge, the electrical field is not well defined. It is considered to be the electrical field around that discrete charge is not well defined. See, why we are saying that it is not well defined? Because it is very close to the discrete charges. That is the reason we are not able to get the Gaussian surface pass through what? The Gaussian surface pass through the discrete charge. And what is the next point? Point number 5. See, an interesting point, this point. See, what is this point number 5 means? This Gauss law is another form of Coulomb's law, and we can apply to charges. We can also apply this Gaussian law when the charges are in motion. Let us consider the first point. What is the first point? The first point given is, when you are considering the Gauss law is another form of Coulomb's law. Okay, another form of Coulomb's law. Okay, another form of Coulomb's law. How you can say that it is another form of Coulomb's law? See, what is the formula that we have got? We have got it out as flux available phi E is equal to, this is a proof which is not available in your book, phi E is equal to closed integral of E into dA, which is equal to the charge enclosed Q divided by the permittivity epsilon 0. On simplifying this, I can write like this: E into A is equal to, on integrating dA, I will be able to get the total area A is equal to Q enclosed divided by epsilon 0. So, how I can write this? If I am considering this Q enclosed, see, first of all, in order to write this, I will be getting a diagram like this. I have to consider a positive charge. Say, around this positive charge, I will be taking what? I will be taking an imaginary surface. Okay. See, instead of this plus Q, I have taken this Q enclosed. I can say like this: instead of plus Q, I am taking it as Q1 means, then I can write this as Q1 divided by epsilon 0. So I can write E of A is equal to, what is this value? Q1 divided by epsilon 0. Now, what is the value of what? What is the value of this E? See, I can write this value of E like this: E is equal to Q divided by epsilon 0 into A. What is that Gaussian surface? See, here it is Q1. The Gaussian surface is a spherical surface. So I can write Q1 divided by area is 4 pi r square multiplied it with epsilon 0. Okay, but we know that the electrical force, or I can write electrical field E is equal to force per unit charge. Therefore, I can write F is equal to Electrical field E into what? Electrical field into E into Q. So now what I am going to do is, now I am drawing the second again. So I am taking the plus Q1 here. Now I am removing this Gaussian surface and I am placing another charge here. Okay, I am removing this Gaussian surface and I am placing another charge here, Q2. Why I have removed this Gaussian surface? In the previous point, we have stated a Gaussian surface cannot pass through a discrete charge. Here Q1 is on charge and Q2 is on another discrete charge. So if I am drawing a Gaussian surface, the Gaussian surface cannot pass through Q2. So I have removed this Gaussian surface. Now, if you just consider the distance between Q1 and the Q2 as R. Now, if you are taking F is equal to Q divided by E into Q, what is the electrical field at this point due to this Q1? But we know that the electrical field E due to this charge Q1 at this point where Q2 is placed is generally given by the formula 1 divided by 4 pi epsilon 0 into Q1 divided by R square. You take this value and substitute it here. Therefore, the force F is equal to, what is E? It is 1 divided by 4 pi epsilon 0 multiplied it with, see, Q1 divided by R square. Okay, Q1 divided by R square. Okay, Q1 divided by, it is considered to be R square. So not R2, it is taken to be R square. Okay, I am taking this as R square, multiplied it with, then Q. Instead of Q, here I have placed another charge called to be Q2. So, therefore, in between the two charges, what you are able to get? The force available, F equal to 1 divided by 4 pi epsilon 0 into Q1 into Q2 divided by R square. This is nothing but the Coulomb's law. So we can say that Gauss law is treated as much more general law than Coulomb's law. So therefore we can state that Gauss law is considered or treated as much more general law, much more general law than Coulomb's law. One more point. See, here also I can state another value or another note. See, where I have stated that Gauss law is another form of Coulomb's law. And this Gauss law can be applied to charges which is in motion. Not only the charges are rest. For the charges are at rest alone, the Gauss law is not applied. For the charges which are in motion, that also we can apply this Gauss law. So let us consider it as a note. What is the note? See, I am saying it as like this. Gauss law can apply to charges. Gauss law can apply to charges. Gauss law can apply to charges when they are in motion also, while or when they are in moving or in their motion also. This we are calling, or this we are considering it as the important discussions regarding the Gauss law. Thank you.